All right, so I think we're ready to start our colloquium today. Welcome, everyone. So we're happy to have today Professor Sascha Husa, who's been lecturing this week in the ongoing school on various aspects of gravitational wave physics. I understand he studied at the University of Vienna, and he's currently a professor at the University of the Balearic Islands in Spain. He's a member of the International Society on General Relativity and Gravitation and of the Spanish Society for Gravitational Relativity. He has also a number of collaborations with various groups like LIGO, GEO. He's, I understand, also been involved in the Einstein telescope design study. And his research is, has emphasis on the finding full solution to Einstein's equations using numerical methods, which of course is a rather important subject in making the connection between GR and the, in particular, recent observations of gravitational waves arising from black hole mergers. So today, he's going to tell us about modeling the gravitational wave signal from compact binary coalescence. Thanks.
Thank you very much for inviting. So no differential equations, all right? Okay, so the very, very basic idea of how gravitational wave data analysis works at the core, it technically, I'm quite sloppy, but the basic idea is the same that if you're in some bar in Sao Paulo tonight and you hear some music and you want to know what's this song, I want to know what this is, and so you take your cell phone, you record with Shazam or some other app, you record the sound of both the music and the noisy bar with all the noise, and then there is some server somewhere which compares your recording with a huge database of all the possible songs. It tells you what the most likely one is this, the second likely this, and so on. Okay, and so that you need some method to compare, for example, and you need this catalog. And the basic idea for gravitational wave data analysis is just the same. Somebody has to provide this catalog of what are the possible signals that we might listen to, according to the Einstein equations in particular. And so somebody has to solve the Einstein equations for all the possible sources that are interesting, or from a particular class. I'm mostly interested in black hole binaries. And then prepare some kind of catalog of these waveforms, where catalog in reality is some code, some C code, some numerical code, where you tell the code this masses and these spins, and then it tells you what's the waveform, and then you can compare this with the data and find out, use some statistical methods to find out which one fits best. Okay? So I'll talk a little bit more about how these things are used in the data analysis, and I'll talk about how we solve the Einstein equations, how we make these models, and at the end I'll give you some news results very briefly about the new gravitational wave transient catalog, which was released last Saturday. All right, so this is a snapshot of the gravitational wave propagating through space-time in some binary black hole merger. You see this kind of spiraling motion. But we actually, what we have to model is something like this. This is the gravitational wave signal plotted as a function of time and as a function on the celestial sphere of the angles. Okay, this is really the thing that we have to model for all possible astrophysically relevant coalescences. All right? So the challenge then is to do that, to model the gravitational wave signal, this kind of object, for astrophysically plausible parameter space of all coalescing black holes, neutron stars. First, of course, we focus on general relativity. Eventually, we want to do this for alternative theories of gravity and compare what fits best. In general relativity, there's something which makes things much simpler. As many of you know, there's the Noether theorem, which tells us that black holes are really very simple objects. Astrophysical black holes, they're described, their masses and their spin vectors are very clean objects. And a binary is described by 9 dimensionless parameters. There's a dimensionful parameter, the mass, but this is just a scale parameter. You can put that it's important for the observation, but you don't have to consider that when you're modeling it, when you're solving the Einstein equation. So this is the mass ratio, the spin vector, so 2 times 3 components. And then if you're quasi-circular, have quasi-circular orbits, you're done. If there's some eccentricity, you need 2 more parameters. So we have a 9-dimensional parameter space of intrinsic parameters, plus what we call extrinsic parameters. Question? Sorry? Well, we assume that that's fixed, such as the speed of light. It's not something that we vary. I mean, you could, of course, if you want. Sure, the 2 black holes interact. It's GR. Yeah, but it's not one of the parameters that we investigate across the parameter space. It's a parameter of the theory. There's a different context.
Try to interpret Nathan's question. So because you said that you're scaling out the total mass, but with that total mass with respect to the Planck scale, it's it's a ratio, right? So
let's take the time. So I'm talking about general relativity. It's a classical theory. There's no H bar. H bar is tremendously interesting. We would love to have to observe some quantum gravity effects, and eventually people will consider some alternative theories which have H bar, and they discover some quantum gravity effects. But I'm not going to talk about it today. I'm just dealing with GR, which has the fundamental parameters G and C, and then a particular system that we consider also has a total mass. GC and the total mass, they enter these calculations in a very trivial way. They're just fixed parameters. But the interesting thing that we have to solve for is how it depends on these dimensionless ones. Okay? These are varying across the parameter space and make the signal look very different depending on where another thing would be interesting to see what happens if you change C a bit and you change G and you go away from GR, but I will not talk about all these very interesting aspects. All right, so there are some requirements to do this. So there's certain accuracy that we need. And this is a slipping target because the detectors, they get more accurate all the time. So what was accurate enough last year isn't going to be accurate enough now, and then has to be improved further next year. So we constantly have to improve things. And then these models, these codes to evaluate the waveform, they actually have to be very, very computationally efficient because the statistical method to use them is a Bayesian inference, which has to evaluate your model many, many times, tens of millions of times. And so this is computationally quite expensive, and in order to do this in a reasonable time, we have to evaluate our model very, very fast. And then another thing we have to ask, I'll talk about this a bit, is how accurate, once we have a model, how accurately can we actually measure different parameters? Are all these 9 parameters the same? Can we all measure them with the same accuracy, or can we measure some more accurately than others? Eventually, as the detectors become more accurate, all of them can be measured better, but at the moment, our opportunities are quite limited. We don't have to know a lot about gravitational wave data analysis, how it's actually working. One thing that's worth knowing is, particularly if you want to read the papers, is the workflow has really 2 steps at the moment. So the first step is what we refer to as searches. And so they give you detections. They tell you that what's the statistical evidence of having seen some signal above your background. And for this, you use a fixed template bank, use a fixed grid to find whether there's something like this. This is a picture of this template bank as it's used in mass 1 and mass 2. And you see there's this grid, which in some regions is denser, in other regions is not so dense. It's carefully crafted to be just dense enough, but not too dense so that it will be more expensive. And as we use this for the searches. But once you say, okay, I have this 5 sigma evidence that there's really an event, we go to stage 2, which is Bayesian parameter estimation. What I should also say is there's a different pipelines to do this, different codes, and of course they cross-check results, and this is a very, very important problem in big industry. But once you have a detection, then you want to find out what's the best statistical statement which I can make, and then you somehow adaptively wander through your parameter space. You find what is the most likely template and what's your error bars, and then you get pictures like this. In this case, this is for the final mass and the final spin parameter, so curve parameter, which goes between 0 and 1. And you get these probability distributions for example, the final mass, and then here for both quantities together. So here you have a 50% and 90% likelihood. And what you see is that, so now, in doing these calculations and trying to find out what fits best, you have to use different models. You see this here. There's one model which has a funny name, IMR phenomena, another one with a funny name, EOBNR. And you can see, and then there's an overall thing. And you can see that in this case, very nicely, they pretty much agree. They don't give you exactly the same result, but they pretty much agree. So we are quite confident that we have a good estimate of the best value of a final mass, and then we have derived our error bars. Okay, yeah.
Okay, can I ask, so for the first observation, so it falls in that region up there where there is so the low density of points, so there seems to be an isolated. I'm wondering if did it have an impact on the precision you could get from this, having only this template there?
So this template bank is designed just to have basically the optimal efficiency for the detection. And so it turns out if you have very low masses, then you measure many cycles, and in principle you can measure your parameters very, very accurately, and so you need to put very many time plates, because just making a small difference.
Yeah, I'm just wondering, so by accident it happened that the first observation, okay, whatever, it's up there where, according to this plot, the density is not large, right? So if I'm reading this correctly.
So I'll explain why this is.
Yeah, no, I'm just, sorry, I understand that you have your reasons to do it like this, but I'm just wondering if the fact that it happens to be there, and I imagine that you didn't have too many templates around it to compare to, whether it had some impact on the precision you could get from.
No.
Okay.
No. The thing is, it's just the right number. Okay, and so the explanation is why we have so few here and so many there is because, so if you have a low mass, you have many cycles in band, and so in principle you can determine your parameters very, very accurately. Okay, and so if you just change your parameters a little bit, there's a big difference in how this template is seen by the detector. And so you have to you space your templates very, very finely. But if your mass is larger, you have few cycles, they have less information, and so basically a template, this template, in fact, for the detector, looks pretty much very similar to this one. Okay? So while here they look kind of coarser than here, for the metric that your detector uses, they basically have all the same spacing. Does it make sense? All right. But also, so just to emphasize this, is basically what this gives you is what's the probability of having found something. And people then can discuss a lot whether it's 4 sigma or 5 sigma. But once we think there is something, then we use this other method, which is much more precise. And this is what really tells us what we think we have seen. And so I will not speak much about detection. I will focus mostly on parameter estimation, which depends much more sensitively on how accurate the model is. Okay? So if your model is not so great, in some vaguely defined sense, you will still detect that there is something. But but you will not exactly know what are the masses and the spins. Here, the details matter much more. Okay. So what are the basic methods that are used for this kind of data analysis? Essentially, there are two basic types of methods. One is basically time frequency pattern recognition, or methods which look whether there's some excess of signal of a certain shape. So you see this, probably you have seen these kind of time frequency maps, maybe associated with the gravitational wave detections, so time and frequency, and then the brightness is how intense it is. This is one way, but the optimal way to do it uses what is called a matched filter. So this is basically you form some kind of scalar product, some integral between the detector data and what's your template. And then when the scalar product gives you the best value, there you have the most likely detection. So this is let's try to see the movie again that tries to show this. So here we have our detector noise, a lot of noise, and then much smaller is the signal. All right, doesn't look like a black hole, but okay, this is our signal. And so now what we're going to do is we have a template. This was a little black thing. We shift in time and compare with the data, and then we carry out this matched filter calculation, this projection. And so here we get some signal because there's this noise, but it doesn't match very well. But as soon as the shapes coincide, then we get a large result. And if this is statistically significant enough, then we say, okay, here we have a detection. So let's look at this little movie again, if this is possible. Yeah. So now we shift our signal relative to the data, noise, 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 and then once they coincide in shape, you see that they didn't have to coincide in amplitude. Then we say, okay, now we have something. So so both methods. So this is the most efficient one to identify in particularly short pulses. There's not a huge difference in efficiency. This is just a little bit better. But in order to identify the sources in this kind of Shazam, very vague Shazam sense that I indicated before, this is your method of choice. So this is all fine, but now, of course, the identification of your sources, of course, is limited by the sensitivity of the detector. So the best things I'm arguing to have more science, make the detector more accurate, more sensitive, but also the accuracy of this model. So we have to have very precise description of how the waveforms look like for different types of sources. So now let's start waveform modeling, like really simple, waveform modeling 101, and look at the simplest possible approximation of the signal, which is take Newtonian point particles in Newtonian orbits, but now they lose energy due to the quadrupole formula, which in fact is one exercise that the students are doing this week. And so then people like, well, it has been done a long time, but people like Jan, for example, then they calculate this analytically, and they will find the gravitational wave polarizations and how they depend on the distance to the source, G and C, the frequency, and we can write down this result. And it has this characteristic quadrupole wave shape, because this is the quadrupole, the leading order information, which is the quadrupole content of the waves. All right. Then we can write down, for example, so this is the radiated energy, power, E dot, a leading order again. So we have our C's and G's, and depends on the frequency. But then we see that on the source parameters, like in this case on the masses, they only depend on this one quantity MC. It's called the chirp mass. It is a particular combination of the masses. So in all these formulas, everything just depends on this one parameter. So therefore, this is the parameter which we can measure. We can't measure with this formula the individual masses. We can just measure what it depends on, which is everything gets lumped into this one parameter. So if we, for example, have gravitational waves from black holes which are very far away, where the higher order terms don't matter, what we can measure is simply only this parameter. All right. So here, well, in fact, here we have the picture that goes with it. This is the binary neutron star detection from a year ago, which is basically low mass. It's all in spiral. This is the chirp signal, how the frequency ramps up. This is the h plus, how this looks at a function of time. And so if basically our signal is really coming from the in spiral, then, so if it would be black holes, we can just measure this. For binary neutral stars, which can be deformed, we can also say something about their deformability. So we see, so this is degeneracy, which is one of the big topics in gravitational wave data analysis. What is good for searches is bad for parameter estimation. The fact that we have everything depends on a single parameter, it makes searches easier. But for parameter estimation is not great because it limits the information that we can learn. So this was a very simple example, but this topic, this theme, goes through the whole topic of gravitational wave data analysis. Here we see another example. This is the lightest black hole, not the lightest binary, in fact, the lightest black hole binary so far. And so here my chirp mass has a different symbol, but this is the chirp mass. You see, this is measured very accurately, 8 plus minus a little bit. Referring the total mass is something between, I don't know, 17 and 22. The error bars are much larger, okay? It's here we have some information for the merger, but it's not enough to tell us a lot about the total mass. But the thing that's measured very accurately is this chirp mass, which we have seen is very low order Newtonian approximation before. If we want to learn more about the sources, we have to dig deeper into the signal, and we have to understand the anatomy of the signal a little bit better. This is an example of roughly what we have seen in the first detection, and we can see these different phases, different physical phases of our coalescence process. So when the two objects are very far apart from each other, there is this kind of adiabatic in-spiral phase, which is very well described with the post-Newtonian expansion. Think of it as writing the quantities that you're interested in, like maybe your Hamiltonian. You write it as the Newtonian part plus some order in v over c, there's a velocity divided by c, plus higher orders, higher orders, higher orders. State of the art is mostly v over c to 7, now going to v over c to the 8. You can do it for the radiated energy or any other quantity that you're interested in. So these are very sophisticated perturbative methods that have taken decades to develop, and we have we had a lecture series about this last week and also one this week. However, this perturbative method breaks down when the velocity becomes comparable to the speed of light, and you can't use this anymore. And then you have to solve the full equations without approximation on a computer. You have to discretize them, solve the full equations. And then you have to do this roughly when you have more than maybe 10 or so solar masses, you have to use this other technique, which is called numerical relativity, where you solve the full Einstein equation on a computer, discretized as a partial differential equation. Once the black hole have merged, things get a little bit simpler again, because as the black hole relaxes to its stationary state, you can again use perturbation theory, linear perturbation theory for a single black hole, and the signal can eventually be described by what is called quasi-normal mode ring down. So our signal is now some series and different exponentials, so these things are real, this is real. So there's an oscillatory part and a damped part. This is a damped oscillation. What is quasi-normal modes? If you have a system which doesn't use energy, you have normal modes. And if it loses energy, there's dissipation, you have quasi-normal modes. So you can use perturbation theory at early times, a different perturbation theory at late times. Since this is linear, it's not telling you the amplitude. And so you have to use computer simulations to connect it all together. Now we have to solve the Einstein equations numerically. So how we do that? Well, these are the beautiful Einstein equations. Everybody loves those. But they are four-dimensional. They are space-time equations. In order to solve them algorithmically, systematically, we want to convert them into an initial value problem. Like, for example, we can write the Maxwell equations four-dimensionally with a Faraday tensor, but for solving them, maybe it's more simple, maybe straightforward, to write them in terms of E and B and an explicit time evolution. So starting in the 1950s, quite late after formulating these equations, people started to write the Einstein equations as a time evolution problem, where you have your space-time here, four-dimensional, you slice it by space-like surfaces, and then you choose one of them as your initial data, and you evolve forward in time. If you choose some coordinate system for your space-time, essentially you can convert this to 10 coupled nonlinear wave equations with pretty complex source terms. But there are some fundamental problems, namely that main one is that GR is a gauge theory, like every other fundamental theory in physics. And so this means that you have unphysical degrees of freedom, you have constraints, you have to make sure these constraint violations, they don't get violated in your time evolution. And you pick up a lot of complicated problems in how to do your gauge fixing appropriately for black holes and so forth. This problem took about, so people studied this in the mid-60s, and it took about until 2005 to have the first breakthrough. These are pictures of the first simulation that actually worked, the first orbit, where you see it's more like half an orbit. And so the waves are really just the merger signals. There's no in-spiral here. But it was pretty clear that now this works, and now people have just to refine their methods. There was a big gold rush of improved methods and results. So also note that the first detection of gravitational waves, it just came 10 years after this. So 10 years, this is like 3 PhD theses. So we had 3 PhD theses to go from this very poor calculation to having enough accuracy across a wide parameter range to correctly interpret the first detections. Now, there's another problem involving black holes, namely the general relativity has singularities. So black holes are not the problem, but there's inside there's a worse issue, which is that there's a singularity. I mean, computers don't do very well with singularities. They don't do well with infinities. So we have to somehow cut those out of our simulations. So how we do that? There are two methods to somehow avoiding your interior. The first one is usually called the excision technique. And so what the basis of this is that since the black hole has a horizon basically means that all the information is flowing inside. In numerical analysis, this is called a pure outflow boundary. Here's like an inflow boundary. This is where the apparent horizon is, basically. And so if we just cut a hole in the computational domain, we don't have to put boundary conditions because all the information is flowing inside. Okay? That sounds like a great idea. Problem is this is very, very complicated because so when you excise this hole here, if you excise outside of the apparent horizon, this doesn't work. If you do it too far inside, you're too close to the singularity, also doesn't work. So this evolving black hole, you have to keep the excision surface very close to the horizon, just in the right place. And this is very difficult, and there's only one code which does this. Very sophisticated control systems are keeping this excision surface in place. There's another method, which is called singularity avoiding slicings, which does also excision, but not in space, but in time. So if this is a cartoon view of our space-time, so time goes up, space goes here. This looks like a flat slice. But now what we can do, we can choose our time coordinate. In GR, we're completely free to choose our coordinates as we like. So now we wrap our time coordinate around the singularity. We just slow it down here, so that simply our time coordinate never reaches the singularity. So we don't never reach it in time, and we don't have to deal with that. Okay? Now, this may sound a bit like science fiction because it looks like your geometry is going to get extremely distorted. And that also doesn't work. However, it turns out, and this was only shown after 2006, so about half a year after this first breakthrough. In fact, if you do it the right way, you can write this down in such a way that the metric is completely time independent. The three metrics completely time independent. Nothing gets distorted. Everything is nice. And so most groups use this because it's much easier. And then one code uses this method. So this is how we.
Yeah. Is there some intuition for why? So the statement that you can find this time-independent method. It's kind of surprising, right? That you were.
Yeah. So there was a theorem which says you can't do this, but But so I saw a movie of the first merger, like this movie. Okay, no, shorter because there were much shorter simulation. Basically, just this part. Okay, I just saw a movie of this part for the first time. I thought, wow, there's very complicated coordinate conditions, and they beautifully freeze into something which is time independent. So what I have to do now is I have to go and derive this analytical solution, and we can study this and see how this works. Okay, and then about half a year later, I had time. I went and derived this analytical solution, but there was a theorem basically that you can't do this. But once you've seen it in a movie, you think, well, maybe the theorem is not correct. Okay, and then you just go and derive this. And I will actually talk about this tomorrow in the class, in the lecture. All right. So this is one method, just to cut a hole. All the information is flowing in. This is the other method. This is one of, oops. This is not a movie. This is just a snapshot. Even better. Takes less time. So here you see, so what's plotted here is what we call the lapse function. Basically, it's a function which tells you how fast time is flowing. And you see where you don't see this, you don't have a good angle here. It's my fault. But you can see that there's this dip. So this means that just where the center is of this thing, where your time flow really goes zero. You're stopping your time flow, and that's why you never run into the singularity. Okay, you get these very nice, very regular shapes, and everything is fine. Yeah. So the color means that so red is 1. So far away, your basically time flow is 1, like in Minkowski space. And then as you go closer to the black hole horizon, time flows slower and slower and slower. And in the center, you make the time flow 0, which really stops the physical progression of time. You never run into the singularity. And it looks perfectly regular. There's no complication. But it was very surprising for people. But this is at the root of why this whole thing works. Okay. Now it moves. Now it moves. Excellent. So you can see this is just very regular. It gives together with the previous movie, it gives you an impression. People thought this is all going to be very complicated, very difficult. But in fact, this is really taking two time-independent black holes, and they very calmly move around each other. If you consider general problems of solving the Einstein equations, basically binary black holes is like the most simple thing to do. One of the simplest things you can do. You can imagine many situations that are much more complicated. We have no clue how to solve them. We can solve this.
Just one more question.
Yeah.
So the first part in the movie, so that part you can compare to the post-Newtonian?
Right. Compare this to the post-Newtonian. Essentially what you find is, so post-Newtonian is extremely accurate. It works extremely well. Okay? And roughly, I would say, down to on the order of like 10, 12, 13 mass units. Right, so for Schwarzschild, the horizon is at 2 mass units. So down to maybe a distance of about 12, 13 or so is really extremely precise. And then you see it degrade pretty rapidly. And then when you just a few orbits for the merger, this gets really bad. Okay? But because I'll talk about this a bit more afterwards. I'll have another slide. I'll talk about this. Now, if you want to put this on a computer, there's a number of more problems. And one is that, so one of the nice things is that the Einstein equations actually have, apart from the singularities, they have smooth solutions. If you add fluids, you can create shocks and all complications. But as long as you don't do fluids, then the solutions are smooth. You can use high-order finite differencing methods, spectral methods, but you have a number of different length and time scales. You have the individual compact objects, black holes, or black holes are the most compact objects, so the most extreme small scales. You have the orbital scale. The wave frequency increases during the evolution, maybe a factor of 10 or so. Or the wavelength scale. You have the fall-off, long-range fall-off. You have the outer boundaries. You need many different scales to resolve, and so you need both spatial and temporal mesh refinement, which makes your computational infrastructure quite complicated. Even with these computational tricks, so for here, this is the outermost grid. Your actual binary is somewhere with a tiny dot in the middle. You have to go very, very far out, resolve many different scales. But even with these tricks, a typical simulation costs between about 100,000, maybe 1 million core hours. So these are expensive simulations. You have to space these simulations quite coarsely to sample your parameter space. I have this rough estimate. I would say roughly the whole field, maybe the last decade or so, maybe is spent on the order of 10 to the 9 core hours. I think I would say personally I've spent around 100 million hours. Okay, this is expensive. All right. So we've talked about
Where do you run this simulations? Is it in the clusters in Spain, in the US?
So we don't have access to US machines. So what I use is so there's in the US you have this Exceed network of tier 0, and in Europe there's something similar which is called Prace. So you have to write grant proposals to run on these big machines. There's one of these Prace machines is in Spain. So there's one of the top computers in Spain. We run on this one. We do test runs on smaller ones, but production we need really big ones. All right. Now, so how long is this going to take? It's all very expensive, but if I want to start like at half the frequency or twice the separation, how much more computer time do I need? Well, Post-Newtonian gives us a simple estimate of the coalescence time. Well, basically, this is the symmetric mass ratio, this quantity. And then this is the initial frequency. This is roughly a power of -3. So if you go to half the frequency, you need roughly 8 times time, which is roughly 8 times the resources or more. So if you can do 10 orbits, doing more orbits at low frequency, it's very expensive. It's not feasible. And so what you have to do is you have to glue, to get the complete solution, you have to glue your last orbits together with the post-Newtonian waveforms. You take the post-Newtonian analytical one, which goes all the way to as low frequency as you want, and then you glue them together, and then the rest, the high frequency part, comes from the numerical simulation. If you want to see this compared to the detector sensitivity, so we have this here, we have some of these noise curves. This is an old plot. So this would be roughly advanced LIGO sensitivity. And so we have the tracks of different black holes with different masses. If the mass is lower, we go to higher frequencies. For this very heavy black hole, numerical relativity covers the whole regime. But this is very heavy, 240 solar masses. For something more realistic, numerical relativity just covers this part, and the rest, the low frequencies, we get from post-Newtonian. So now we do this for one waveform, and we have one point parameter space. All right. So eventually we need a model that describes the whole parameter space. From some isolated points in our 9-dimensional space, we have to infer what the general formula is. But before I talk about this, let's talk about a few further complications and how to simplify the complications. So up to now, gravitational wave data analysis, which this is an old slide. This was applicable maybe half a year ago, not quite anymore. Data analysis basically only used the quadrupole mode, so m equal 2 spherical harmonic, which dominates the signal. So this is what here, this plot, this would be this red curve. And if you look at a binary face-on, this is really what dominates everything. And this is where they have the highest amplitude. But if you look at a binary from the side, then other modes, other spherical harmonics are also significant. So for example, if you would look at a binary from an inclination of 70 degrees, you see that the signal is smaller. So we're not going to see this now, probably. First, we see the signals which are really loud, which we see face on. Eventually, we're going to see those as well. And you see that the wave signal is much more complicated because it has contributions from other modes. Okay? Some So there's a lot of effort now. Oops. This is from a different talk. Okay, there's no poster by this guy. All right, sorry about that. He's not here. There's a huge effort in LIGO now to basically incorporate higher harmonics into the analysis of O3. What people have done is somehow map out roughly where this is going to be important for detection and for parameter estimation. And it's basically where it's important is for larger mass ratios and large masses. Okay, which at the moment we have mass ratios pretty close to 1, and mass is not so large. So it's not a very big effect, but we certainly want to include it to squeeze out a little bit more precision. Also, the accuracy of the waveform models is not just important where you have an event, but also where you have no event. Because then with this you can exclude that, for example, we measure binary with a mass ratio of 1.5, for example. At mass ratio 1.5, higher modes are completely irrelevant. Why do I have to include them? Well, because to test that it can't be at higher mass ratio, because the higher mass ratio, if you don't include the higher modes, we have some degeneracies, and only if we include the higher modes, we can see, no, it can't be at higher mass ratio, it really has to be close to mass ratio 1. So that's why we really need them, even if for the actual binary we have, they don't give much contribution. All right. So one of the important things also for the data analysis is basically, if you have just a quadrupole, it's very hard to measure what's your inclination. And so if you look, because most of the waves go out face on, if you don't look at it face on, it's not as bright, and so you will be confused about the distance to the binary. If you want to break the degeneracy with the inclination, you also have to include the higher modes, and that will allow you to more accurately measure the distance, which of course for astrophysics and cosmology is really important how far these things are away, particularly if you want to map out the universe. Another thing is if your binary is asymmetric, I'm not sure now if I have another, no, just have this. If your binary is asymmetric, then you will radiate more waves in one direction than in another direction. And so this will create some kind of recoil effect. It's basically like if you have a garden sprinkler and this is... There's more water going out here than there. The thing is going to hop across the lawn if it's not symmetric. And the same thing is going to happen with black holes. And one of the things that we have learned in the last decade is that, in particular, have spins. This can be very large, and you can create recoils of 2,000 or more kilometers per second, which in principle can eject the binary from its host galaxy, which is a very interesting effect for astrophysicists. All right, see, here's the picture that I forgot with a small black hole, big black hole. You have this asymmetric radiation, and you get this recoil effect. Okay. Another thing is spins. Spins are responsible for 6 of the parameters, so somehow the majority of our parameters. So we are going to deal with those. The basic physics of spins we can understand by just looking at the leading order post-Newtonian effects. So the leading order Hamiltonian. This is a spin orbit effect. We have some effective spin, which is basically like the total spin of the 2 black holes with some factors. And so the Hamiltonian is the scalar product with the total spin with the angular moment or angular orbital momentum by some power of the separation. And the spin also changes with time, so ds by dt is the cross product of these 2 things. So what's the effect of that? So the effect is that when the spins are orthogonal to the orbital plane, and this is 0, and the plane is preserved, and your orbit looks like this, up here, kind of boring, the orbital plane is preserved. But if you have spin components in the orbital plane, then this term here will make the spins precise, and will make the orbital plane precise, and you get something which looks a lot more complicated or interesting. Okay? So that's the dynamics, and that's the waves. You see that has a lot more structure than this thing here. In reality, of course, these effects are all much more complicated. In post-Newtonian, you have many terms, and then in full GR, you have other effects, but the basics is described by this very simple physics. So essentially, the leading order effect here is this one, so that the total spin, you can also write basically this kind of parameter. So these scalar products of the, oh sorry, there's a 2, I'll read this here. So S1 and S2, obviously. So in many of the papers, you look at the results, you will have this spin parameter, which is called chi effective. It's just this. It's basically like your total spin appropriately weighted. That you can measure very well, okay? What we can't measure, for example, here, you can see that just with the chirp mass before, this doesn't depend on the individual spins, just depends on the sum. So what you can measure well is the sum, but not the individual ones, okay? So you can measure this. We have plots about this in the papers. The spin difference, not yet. We would have to have a much more sensitive detector. If we have this precession, again, you can define some dominant precession spin, which we have done a while ago in this paper. And again, this is something which I'll show you plots afterwards. At the moment, we can measure it, but we measure this very, very poorly. All right? Now, another thing that is quite scary, apart from some spin components can't be measured very well, is there's this hugely complicated signal. We have, now with precession, you have 7 dimensions. One numerical simulation in the 7-dimensional parameter space costs you 500,000 hours. And that doesn't look good, okay? It doesn't look very good for somehow exploring and describing this parameter space. So we need some tricks. So this plot goes now with measuring the spin components. You see, this is chi effective, where it's a kind of a broad curve, but there's some, between 0 and 0.2, we can measure something. Whereas in the chi-p, the one about precession, this is very, very broad. Essentially, we have no information about whether it's precessing or not. Okay? Not yet. We need more sensitive detectors and more sophisticated waveform models to pull out this information. Now, so I said, precession is really complicated. People were very skeptical. You can do something with this. However, there's a trick. And the trick is that the orbital timescale is much, much smaller than the precession timescale. Okay? Gravitational waves are produced by accelerated masses, so the acceleration that's due to the orbital motion is much, much larger than the acceleration due to the orbital plane slowly moving around. So this doesn't create much gravitational waves. Basically what it's doing is as the orbital plane is dancing around, it changes the direction, the main direction of the waves. So now more waves go this way, afterwards more waves go this way, but it doesn't contribute much to how much energy you radiate, and therefore it doesn't contribute much to how fast these objects move together. Okay? So that's why maybe we want to separate these two effects, and so what you can think of that if you would imagine going to like a co-rotating coordinate system, a co-rotating frame, this would just, a precessing binary would just look like a normal binary, non-precessing one. Okay? So let's use this observation, and we're going to use the following. So now, precessing binary, very complicated waveform, looks very complicated. So what we're going to do now, to have a simple model, we just make a super accurate model of a non-precessing waveform. Okay, we have to spend that effort. And then, because precession basically just gives this kind of lighthouse effect that once we have sent more this way, then more this way, but this is kind of a slow effect. We don't have to add this very, very accurately, and just doing this in a post-Newtonian way is okay. So basically what we do is, in post-Newtonian theory, we compute the Euler angles of making this rotation, and then we use them to twist up our non-precessing model. This doesn't include all the physics. There are some asymmetries that it doesn't include, in particular those which are responsible for the recoil. So some interesting physics is lost. But at the moment, for data analysis, this works very well. And so we have just done precession with a simple trick. This is what we use in the actual data analysis. All right. Okay. I wanted. There are many movies here. The only one that's really interesting that I wanted to show is this one here. Look at the spins of the two black holes. You see they don't move very much. They basically behave like gyroscopes with small corrections. They pretty much point in the same direction. Until right at the end, then there's a lot of interaction. Then they snap. Okay, and then that's where things get really complicated too. So at first they're suddenly there's a lot of dynamics. So these are things that are still very difficult to describe. Okay. So how do we do the actual modeling? Okay, I've said that. So there's a If you don't have precision, it's trivial because there's a discrete symmetry. So if there's no precision in the initial data, it has to be orthogonal to the plane. If there's precision, complicated.
But in that, you didn't have precision.
So it turns out that even with precision, even while there's a lot of complication, in the end, usually it pretty much points, but this has complicated reasons.
So the result is the same as not?
It's not exactly the same, but within the 10 degrees or so. Okay. All right. So now we said, okay, precision, we have a trick, but we don't have a trick for non-precision cases. It's still three-dimensional parameter space, mass ratio to spins. How do we do that? So now I want to explain kind of how we approach this. Waveforms, these are these wavy functions, how we model them. Well, first we choose like simple functions. Maybe we split the waveform into amplitude and phase, or energy as a function of frequency, or radiated power, or something which looks like a simple function. And then we have to decide, I'm going to do this in the frequency domain or in the time domain. So time domain is kind of naturally suited to solving the Einstein equations, but for data analysis, it's often more useful to have the frequency domain. It's because the detector response is naturally defined in the frequency domain, so this makes it more natural, makes it faster and easier. Then we somehow have to discretize these functions because we can only model discrete freedom. Either we make some ansatz, which has some coefficients, or we simply grid it up. These are simple enough functions. Maybe 30 grid points is enough. Or we have some basis functions that could even be constructed from the waveforms, but some process of discretization. So, for example, you want to make a simple model. Just take your function. This is the amplitude, for example, and rescaled in a nice way in the frequency domain. This is frequency. This is a simple function. Grid it up 30, 40 points. Make a polynomial interpolation in the parameter space. Reconstruct the waveform as a spline. It's going to work fine. Maybe it's accurate enough for current detections even, roughly, okay? But we can do something much, much smarter, which addresses the principal problem so that you want to avoid both underfitting and overfitting to all kinds of artifacts in your data. You want to avoid underfitting. You want to pull out all the information that your numerical data have. You spend 50 million hours, make a fit which pulls out all the information, but don't overfit to systematic errors. So this is the big challenge that we're facing in making these models. And there are three main strategies to do that. There's the effective one-body model, which essentially pushes perturbative methods as far as possible. And so you model with the energy and the flux of the particle, and then you're left with some ODEs that you have to integrate. This is quite slow. And then you have to do another model on top, which just speeds up the calculation. Then there's something which is called phenomenological models. They attempt to give you piecewise closed form expressions. That's very fast. And they focus on the phenomenological understanding of what's going on. And then there's other things which are called surrogate models. And basically they focus on algorithms to interpret a particular parameter space, but not so much in the physical intuition. But there's a lot of convergence between these different approaches. At the moment, essentially all the analysis is done with this model plus this one, and then people cross-check that they give very similar results. All right. You also need some kind of hierarchical strategy to conquer your parameter space. So what have people done? Everybody who does waveform modeling, we start with one harmonic. We forget the spins. We just consider mass ratio. We start one dimension, one harmonic. Waveform looks simple. And then we go more and more complicated. We add another spin component, still one harmonic. We have more harmonics. We have a higher dimensional space, and so on. We go to the full non-precessing space. We extend to precession. We extend to matter. We start to do eccentricity. Slowly, slowly, people add more and more physics. Where we are current, so we have basically what these things are things we've done. What's currently happening is basically what's not yet finished, calibrating precision effects to numerics, the full generic space. There are lots of challenges still remaining. And then, of course, you are currently doing this for GR, but eventually you will do the kind of similar program also for theories that go beyond GR. All right. So this is my disclaimer slide. So what I am working is this phenomenological waveform program. So this is a number of universities that are collaborate, and so that they have these models have funny names like Phenom D and Phenom P. And you may see these. Usually they're called IMR phenom something in the papers. And so this is one of the models which is used for the results, for the data analysis, and developing it and coding it up. This is what we do. And this is the picture of the computer that we use. This is the big machine in Barcelona, which happens to be in a church. It was recently voted the most beautiful supercomputer of the world, because it's in a glass cube in a church. Okay. All right. Now, so what's my time? So maybe like 5 minutes? 5 minutes. All right. Okay. So a little bit about what we do now in practice. So we say, we take amplitude and phase. We do this simple non-oscillatory function. So this look like this in frequency domain. That's your amplitude. This is your phase, a phase derivative. This is what these kind of things look like. Then we split it. The more regions you split off, the simpler it becomes. But we just take 3 because these 3 have physical intuition. In spiral, we can use post-Newtonian. Ring down, we can use perturbations theory. Intermediate, we can use other things. So for each region, we have a certain amount of intuition. And then you just develop a simple model of these kind of quite harmless functions and model them across the parameter space. Now, so this is what we do a lot of the time. We have these data sets of some coefficient. Can you hear me? Yeah. We combine data from basically all the codes that we can get of data points from different codes, and information sets. They're very noisy. We have to use a lot of effort to control the quality of the data. And so what we have finished, we're just basically finished now. We have done this for all the subdominant modes. So this means you have basically a handful of modes, 5 modes, frequency and amplitude, about 10 or so coefficients each. So we have done about 100 coefficients, modeled about a few hundred waveforms. It took us 2 years to develop these kind of fits, to incorporate physical intuition, and to make sure that we're neither overfitting nor underfitting the data. All right. I'm going to skip some of these things. I'm going to make this. All right. Bing. Nice announcement, which you know all of this very well. This was the binary neutron star discovery last year, which really studied the multi-messenger astrophysics. So this is the gravitational wave detection. This is the gamma ray detection by Fermi. I'm sure you're well aware of this. Just to show you once, to show off this very nice movie. Remind you, there was because we have used three detectors, 2 LIGOs, 1 Virgo, we could really pinpoint this quite well in the sky, more accurately than Fermi, and people have discovered the optical counterparts. South America plays an extremely, as you know, an extremely important role in these optical observations. And This has also been, so sorry, this is still in Spanish, I just realized this before. So this was also the start of gravitational wave cosmology, because by measuring, so you can use this as standard sirens by combining the information from gravitational waves, which give you the distance, and the electromagnetic information from identifying the host galaxy, and measure the Hubble constant. Now you see, our measurement of the Hubble constant is not very accurate at the moment, okay? But it's going to be more accurate with more detections, not just binary neutron stars, but you can also use detections without an optical counterpart and statistically correlate them to the catalog of galaxies. And so what we hope is in the next 10 years or so, this is going to be much, much more accurate and will eventually contribute to clarify the somehow discrepancy between the current methods of measuring the Hubble constant and really contribute a lot to our understanding. Very briefly, but just a simple announcement, the result from the release of the first gravitational wave catalog from the 01 and 2 observation runs. We've previously had 5 gravitational events, 1 sub-threshold trigger, 1 BNS. So this one has been upgraded now. And so we have 11. Now we go to 11. 10 BBH mergers, 1 BNS. The data are open. There are tutorials. You can go there, learn how, download all the data, learn how these things work. And this is this wonderful diagram of all the masses in the stellar graveyard. Blue is what we have observed by gravitational waves. Black holes. These are black holes which we have observed in EM. You can go now and count them. So now with this new release, we in fact have discovered more stellar mass black holes through gravitational waves than through EM for the first time. This is a quick table of all the results. And I just want to highlight one case. So I want to highlight maybe 2 things here. First, so O2 started here. There was a detection in January, 1 in June, and 1, 2, 3, 4, 5, 6 within 1 month. So this was pretty lucky. It was because the detectors got a little bit. And then I want to highlight this event here. This is the heaviest mass, 80 solar masses, a redshift of 0.5, and a distance of about almost 3,000 megaparsecs. So this was emitted about 9 billion years ago with large error bars. The O2 sensitivity, O1 run, O2 run. So you see that some detectors had some problems. Virgo joined very late, but the best detector had increased sensitivity, which seems to have contributed to more detections at the end. There are some plots here. Maybe the only one that I will really comment is this plot. So all these curves are 90% confidence levels. So this is mass, chirp mass, and distance. And so the interesting thing here is that you have, which these two degenerate. And so the distance, so luminosity distance, and the chirp mass, they are roughly positively correlated. What you expect if you don't have gravitational lensing. So there was a big question of, are these maybe lensed? What's going on? And now that we have more events, it looks like it's exactly the correlation that we expect. I have some plots about mass ratios and spins, final masses, but I think I'm at the end, so I'm not going to talk about this, neither about rates estimates. I just want to say something about the future. I think gravitational wave astronomy is well on its way, and fundamental physics. We are thinking about the next generation on the ground, and there's a lot of talk about people hope to have an international network of third-generation detectors. Third-generation gravitational wave astronomy will only happen if there's a large international collaboration. And there's also plans to go to space. So there's a European space mission planned for launch in about 2034, which will observe at much lower frequencies. Things like certainly supermassive black holes, but maybe also echoes from the Big Bang. Well, let's go to this. So there's this, put for the end this plot here. So this is like a brief history of the universe, time and redshift. So we are at redshift of 1/2, somewhere here. But in the future, LISA and the Einstein telescope, they will allow us to go all the way back, observe mergers in the dark ages, and probably, hopefully, observe waves just from the aftermath of the Big Bang. So this is what we want to see in the future. And so with this, I conclude. Much before this time, we will start the third observation run of 3 in April 2019. So stay tuned for some new discoveries. Thank you.
Thank you very much. Questions?
So at what point do we need to worry about the rest of the universe interacting with your gravitational wave coming from the colliding black holes?
What's the effect of the environment? You think more, or the cosmological effects, or any of them?
Yeah, will they affect the precision that you can use to, if you want to go back to the early universe, won't they affect the precision?
So one thing that eventually is going to be a very big issue is basically when you have things that are very far away is gravitational lensing. At the moment, we don't have to take this into account, but eventually, once we have objects that are much, much further away, and we have many more of these effects, there will be influence from gravitational lensing, and that's an important influence of as these signals come through the universe, and we will have to take this into account. This will be one complication, and it's in particular if you want to make inferences about the mapping out cosmology with these observations. One of the big things that people have to work on is these kind of effects and how to properly subtract them. So this is going to be one big thing. The environment, like for example, accretion disks, they don't have much mass. So this is a minor thing that people are concerned for LISA, for example. But this is going to be more a minor thing, probably.
So I have the impression that most of the effort in the search for gravitational waves is based on this template matched filtering, where you have this pre-existing templates based on what we know about what should be binary systems or blah, blah, blah. And then you find, based on this library of known gravitational waveforms, and there you go. But I'm wondering, it is not clear to me if there is effort in the LIGO collaboration of trying to find things which we don't know, waveforms and things that we don't have templates for.
Yeah.
So it's not a Shazam thing, which is using a template of usually bad songs.
Right. In LIGO Virgo, there are 4 search groups. There's continuous waves. They search like for single neutron stars. There's stochastic. They correlate one detector to the other one and look for stochastic signals. There is CBC, compact binary coalescence, which basically uses matched filtering to make the best possible statements about the parameters of the efficiency and the parameters of things we can model. And there's a 4th search group, which is bursts, but they really focus on unmodeled searches. And so that the effort of new data analysis techniques is probably is the largest in bursts. And that the progress that people are making in refining techniques to see things without models is very rapid. Is fantastic. Okay? I haven't shown pictures about this for time reasons. But there's a lot of progress to detect these things. For example, we need this for supernovae. It's a galactic supernova. With these methods, we'll find it. Okay? But for this problem of pulling out the masses and spins of black holes, this we have to use matched filtering.
So as you know, a couple of years ago, there was the fiasco of the announcement of the indirect detection of gravitational waves from the early universe with I think the polarization of the cosmic microwave background, right? The BICEP 2. Wasn't it an indirect inference?
Yes.
The B-mode, the B-mode
right.
polarization.
Mm-hmm.
Yeah.
Right.
Yeah, so well, I guess I know the answer. I guess what you will answer, but who do you think will get there first? Electromagnetic indirect beam modes, or do you think that we have a chance of seeing gravitational waves from the early universe in the near future? By the near future, I mean the next 20 years.
What is
It's a very broad
years?
question. I'm sorry, but I just wondering.
So 20 years, so 38. So says will have run for a few years. I think that the great thing about early universe physics is that at the moment there's so much room for speculation. It's fantastic. So I don't have a guess, but I think what is clear. So by this time there's going to be LISA. There's going to be much more accuracy for high frequencies on the ground. We'll have much tighter constraints. That's for sure. Very, very interesting constraints. Whether people see a signal, I don't want. I think it's yeah. It's quite possible. No, it's quite possible. But well, it's possible. I mean, there's some models which predict a signal for advanced LIGO. Is it likely? No. But possible, yes.
So just to follow up on that, and because you kind of mentioned this in one of your latest slides. So for early universe, one of the possible sources of gravitational waves are, for example, phase transitions, or something like that, which in some cases could fall in the LISA band. You mentioned dark ages. What do you have in mind there?
Sorry?
You mentioned something for dark ages that you could go back to those times.
Well, so one of the interesting questions is, for example, how supermassive black holes have formed. What did they form in some hierarchical way with some hierarchical mergers? When did this processes start?
So
what are the earliest black holes that have been produced and merged in the universe? And so these we should see, these kind of things, if they exist.
Any more questions?
So I just had a comment before going into the dark ages. One thing that I, as an astrophysicist, I think is not stressed to the extent, which is not in contrast with anything you said, is that already the rate of mergers that you're seeing is something that was mildly surprising for astrophysicists to see something like that. It's already in the realm of some of the right side of the models that people had. So this is already extremely informative for us. It's already a lot of very interesting information that people are getting without necessarily need to invoke the past or the past of the universe or other strange scenarios to gain information. This is already very much amazing, and it's, from an astrophysical point of view, is a lot.
All right, so I would say indeed it is very amazing. What you hear people say, sometimes you say that this was a huge surprise. How could we have known? And so from my extremely limited astrophysics overview, I think what kind of happened was that astrophysical models predicted that binary black hole total masses are not going to be very large, 20 solar masses, 30 solar masses, maximum. Okay? And then people realized basically two things. First of all, that if you have very low metallicity, you can have much bigger black holes. And then people realized, with these bigger black holes, you have the merger in band, and you have a lot more SNR, and these are actually gonna dominate. In about, I would say, maybe on the order of 2-3 years before the first detection, this picture changed, and some of the leading population synthesis people, they said, okay, we understand things better now. What we really expect is detections to be heavier black holes, and we predict higher rates, and so the currently inferred rates are exactly within the expectations. But this doesn't take anything away from we're learning a lot about what's happening.
I think
but it wasn't that much of a big surprise.
No, but only 10 years ago, I think there were very little groups in the world that studied binaries at all. And now
so this situation changed, I would say, about 2 or 3 years before the first detection. But very shortly before, yes. 2012. No.
Is there any simulations of the black hole merger in alternate theories of gravity like Brand's-Dick or other scalar tensor theories?
So there are some calculations. So people have started to do this with different types of fields, but it's just not. It hasn't gone very far yet. But I think it's basically at the stage where people start to really restart to maybe kind of make some models. It's really starting. The problem is also that the parameter space is so huge. It's taken us a huge amount of effort to explore one theory, and there's still a lot of unknown about one theory, and we want to understand the whole families of theories. And so I think there's going to be a lot more theoretical work to understand, how can we do this in an efficient way. We cannot explore this infinite parameter space with numerical simulations, but we have to be smart about it. But people are certainly very much focused on going into these directions.
Okay.
All right. So I think we can thank Sascha again.
Thank you.
You're welcome for refreshments, the mezzanine. And I'm not sure what time the school, in half an hour, the students reconvene.